Hello, welcome to the session on improving operational intelligence at scale with Elasticsearch and Kafka. I am Mohan Maturi from Nutanix Engineering, and we have Gabe Contrias from Solutions. In this session, we are going to provide insights into the inner workings of Elasticsearch and Kafka to help you deploy these workloads for peak performance, high throughput with reduced total cost of ownership. This comes from our experience validating a high ingest production workload at one of our large cloud scale customers. And this particular customer had around 800 nodes, total Nutanix nodes, 32 of which are actually deployed for this use case, ingesting approximately 8 billion messages per day. That translates into 32 terabytes per day. So before we get into this session, we would like to understand a little bit about how you're using these workloads in your own environment. If you can, go to the app, the .next app on your mobile device. There's a poll on this session, and if you can answer the first 7 questions, that will be great. So at this customer site, Gabe had the experience of comparing this deployment in Nutanix against a bare metal deployment. Typically, these deployments are actually done on bare metal and all flash nodes. He's going to share us his experiences about the bare metal environment and how Nutanix is going to add value to the workloads.
So deploying on bare metal comes with its own set of issues and inefficiencies. Normally, applications can either be CPU or storage heavy. This leads to stranded resources. Kafka, for instance, needs very little CPU to drive the storage. This means many cores are left underutilized and stranded in their own silo on bare metal. When provisioning applications on bare metal, we tend to over-provision at the beginning, as once you go into production, it takes a long time and can be very hard to add on resources. And this tends to exacerbate the stranding of resources. Firmware upgrades and patches. These can be very cumbersome, and most companies tend not to build tooling around automation of these steps. This leads to very many manual man-hours of individually updating all of these components. When these applications are deployed on production, a lot of the time they're deployed at RAID 0 to get the maximum performance out of the nodes. Now, this means that a single disk failure makes an entire node unusable, and this can lead to hours of Elasticsearch or Kafka being in an unhealthy state. Node failures, again, can lead to many hours of Elasticsearch being unhealthy, as it needs to do a one-to-one copy to replicate all this data out. Application teams should be able to stay where they are most efficient, which is dealing with their applications. But many times when deploying on bare metal, for management and for troubleshooting, they're the ones having to deal with the bare metal instances. Now we'll go over a little bit of an overview of Elasticsearch. Now, normally when deploying these in a large-scale environment, you want to break down each service in its own separate VM. Now, master nodes are basically used for coordination and management. They are neither CPU nor storage heavy. Oops. Coordinating nodes are basically load balancers. They are neither CPU nor storage heavy, but they can use quite a bit of memory. Data nodes are the ones that do the heavy lifting. They are the ones ingesting all the data for indexing and aggregating search queries. They need a healthy amount of CPU, memory, and high storage throughput. Now this is an overview. An index can kind of be considered like a table in a database. And you scale out the shards for parallelism. Now, as you can see, you can have multiple shards underneath. This index has 3 shards and is running at RF3 at the Elasticsearch layer. Here, I'll turn it over to Mohan for the Elasticsearch write path.
So like you've seen in the previous screen, when a request comes to a particular shard, the shards in the red are the leader shards and the shards in the blue are the replicas. When the client writes a request, it writes a request to the coordinating node. The coordinating node writes it to the leader. Once the leader does a task of storing the request, it actually replicates the request to the other replicas. It's actually kind of like a sequential pipeline adding to the overall latency of the request being acknowledged. Now let's go a little bit into the actual write path that actually helps us understand the optimizations that we have done and how Nutanix actually fares pretty good on this workload. So typically to get high throughput for this kind of an application, it's recommended to batch multiple messages into a single batch request. So when the client issues a batch request called the bulk request to your coordinating node, the coordinating node looks at the entire content, identifies the shards the documents belong to, breaks down the batch request into multiple smaller requests and issues to the nodes that actually owns the shards. And the data node takes the request, adds it to its queue called a bulk queue, waiting for a write thread to be configured. Elasticsearch is a very highly customizable application. You can actually configure a lot of these parameters. For example, the number of entries in the bulk queue, the number of write threads, right? So we have done optimizations to make sure it runs better on Nutanix. And one interesting aspect of Elasticsearch is every shard is completely independent from the rest of the shards. It has its own internal data structures responsible for searching and indexing, searching and queries. When the write thread takes the request from the bulk queue, adds it to the in-memory buffer, appends it to a transaction log on the disk, and acknowledges back to the coordinating node. So up to this point, the client has actually got a response to its request, but this data is still not searchable because it's not actually indexed. So there's a timer called refresh interval. At this point, what actually happens is the data in the in-memory buffer is indexed into a Lucene segment. This is what actually contains the data structures for all the indexing, for all the searches. And this Lucene segment is created in the file system cache and the memory truncated. Now this data becomes searchable. So the refresh interval actually controls when the data is available for search, right? So this process repeats with more Lucene segments getting created in the file system cache, right? So all this while you will actually see that the transaction log is actually increasing in size. So there comes a time when the transaction log is large or a flush interval actually triggers. And at this point, the in-memory buffer is translated into a Lucene segment. It's truncated, it's reset, and the segments created in the file system cache are actually force synced to the disk, right? So this is a very important part of the process. So if the operating system kernel has not actually flushed these dirty buffers onto the disk, it creates a huge pressure on the storage subsystem because you're suddenly getting a burst of traffic onto the storage subsystem. And in addition to the write path, there is a background process called merging. What it actually does is it actually takes these smaller segments created during the refresh interval. Remember, the refresh interval can happen at every second, and merges them into a larger segment, deleting the smaller segments. This process continues to happen until the larger segment hits a size of a few gigabytes. So this is what leads to write amplification. Now imagine if you have a segment of 1 meg created during the refresh interval, for it to reach a gig, it is 10x write amplification. So now we understand enough of Elasticsearch. Gabe is going to walk through what we've done at the customer scenario, how we've got a better high throughput on this and the optimizations behind this.
So here we have the key takeaways from this customer's use case. I think the main things to focus on are the 6 million to 8 million documents a minute, the 32 terabytes a day total, and the 3,000 searches a minute, along with having to keep 10 days of that data. This shows you how much data they have to keep around and how much throughput they're going through every single day, and how merging can create even more I/O. So here you can see how we architected this solution for the customer. You can see that we broke out each service onto its own set of VMs, and that we split these up between two separate Nutanix clusters for better high availability. This allows you to lose an entire Nutanix cluster while still keeping your application running. Now, the main thing to look at is that while this deployment required 32 nodes for itself, these were actually split up into two separate 32-node Nutanix clusters, meaning that there were other applications running on the cluster alongside Elasticsearch, breaking down silos for all of these applications. Here you can see in Grafana the two separate deployments. Now, the difference in ingest is due to different Kafka inputs. Here you can see in the Kibana for the Nutanix deployment that during peak times we were doing 135 to 140,000 documents per second of primary data. Now this shows that we're doing over 8 million documents per minute on primary, or over 16 million documents per minute with the replication. I wanted to show you this graph from Prism to show you exactly how much I/O merging can have on an Elasticsearch deployment. At these peaks, that is when merging is going on. So you can see that at the regular times, it might be 10,000 IOPS, but at the peaks, it goes over to 150,000 IOPS, and throughput can more than double just due to merging.
So we were able to get this peak performance by having the operating system kernel continuously flush the dirty buffers into the disk in the background. So in the previous scenario, we've noticed that there is a possibility for all these buffers to be staying in the file system cache and not being flushed to the disk. By changing the kernel parameters, the dirty background ratio to 1%, the data keeps getting flushed to disk in a continuous manner. So literally what we have done is we've smoothened out the burst into a nice straight line, right? And in addition, we make sure there's enough I/O waiting for the the storage level by increasing the NR requests and having the size of an I/O set to 1 meg. In addition, to avoid the merge pressure, we could actually optionally increase the refresh interval. Typically, there are two kinds of analytical applications. One that needs like a quick visibility straight after the data is ingested. So for that, you could set a refresh interval of like a second or a few seconds. But for some that needs like long-term analytics, you could actually increase the refresh interval to 5 to 10 minutes. This avoids the background merge pressure. So in addition, Gabe has actually done evaluation on the high availability aspect of the workload.
So resiliency is where Nutanix really shines for these applications in giving you better performance and uptime. So at the bottom, you can see Elasticsearch settings that we changed specifically for Nutanix that you wouldn't necessarily change for bare metal, as normally when a bare metal node goes down, it is down for a longer period of time, where your VMs on Nutanix are restarting quicker. And what we have seen during this testing is that the data nodes, from the time a physical Nutanix host fails until the time they are back in the Elasticsearch cluster, is under 3 minutes. So this gives you access to that data very quickly. Inactive indexes go green within minutes, and overall the Elasticsearch cluster is green under an hour, where what we saw with bare metal, it could take 6 hours or more before that Elasticsearch cluster is healthy again because of the time it takes to re-replicate that data after a failure. And here I'm going to turn it over to Mohan to go over Kafka.
So typically, wherever Elasticsearch is deployed, you would actually see Kafka being used as a message bus to ingest data into Elasticsearch. And Elasticsearch and Kafka have like very similar data models. And the fundamental use of Kafka is to decouple the producers from the consumers, so that you can add any consumer to the pipeline without necessarily affecting the producer. And so the other good thing about having a message bus in the middle is it actually helps you match the impedance mismatch between the producers and the consumers. Let's say if you have like a slower consumer that's writing to a a data warehouse or something, you could actually add more number of consumers without changing the producers. So coming back to the data model, so just like an index is similar, analogous to a SQL table, a topic in Kafka is analogous to an index in Elasticsearch. So just like you can have shards within an index to increase the parallelism, we could have partitions inside Kafka to increase the parallelism. So think of each partition as a completely independent entity, just like a shard is an independent entity. And a partition is nothing but a sequential log of data. So internally, a partition is broken down into segments of a fixed size, and when when a segment fills up, data gets rolled over into a different segment. So one important aspect to keep in mind is the number of producers and consumers should always be greater than the number of partitions. So that way, you're not actually having the partitions, the producers and the consumers being wasted, because they can only a partition can only be read by a single producer or a consumer. In terms of the deployment, just like a data node in Elasticsearch does all the heavy lifting, you have a broker in Kafka that pretty much does all the heavy lifting. And the partitions are distributed across the brokers. So in this case, like this particular topic has 3 partitions, 0, 1, and 2. The partition 0 is a leader on broker 1, and 1 is on broker 2, and so forth. So the client makes a request to the leader, and it's a responsibility of the leader to actually replicate this to the subsequent brokers, right? And this replication can happen either inline or out of band. Typically, it's done out of band to again keep the latency slow, right? So what we've actually done is in the same customer environment, we've actually compared the performance of Kafka on bare metal against Nutanix cluster, right? This customer had 50 nodes dedicated for Kafka. So just to ingest data into Elasticsearch as well as keeping it for archival reasons. So we have, in this particular case, we couldn't replicate all the 50 nodes. What we've done is we've taken 3 nodes, and for both bare metal and Nutanix, had 1 broker running on each one of these nodes, and actually tested it without throttling it, the max throughput that you can get. So what we observed is that on Nutanix, we were able to get like 1.1 million messages per second in total, and on bare metal, it's 1.2 million messages per second. So the performance is very comparable to the bare metal. And the biggest point to be noted here is that if you look at the broker configuration, it's just using 8 vCPUs and 128 and 32 gig RAM, and it's able to saturate the complete storage. So what it basically means that the 50 nodes that the customer has dedicated for Kafka is literally like wasting so much CPU cores not used for anything else. If it happens to be on Nutanix on the virtualized platform, these cores could have been used to run the Kafka producers, Kafka consumers, Spark, or any of the stateless applications, which doesn't need much I/O. So to get to this throughput, we did similar optimizations. First thing is I'd make sure there's no burst coming out in Nutanix, and actually you could apply these optimizations to any high throughput application that you need. Unlike the databases where the NR request is set to very low number like 4, you typically set the NR request to higher number like 128 to make sure there's always I/O waiting to be serviced for these high throughput applications. The most important thing is that instead of the application doing the fsync, syncing the buffers to the disk, we let the kernel do it. So the kernel can actually rate these buffers based on the data that needs to be synced out. And in addition, we've actually done a TCO for both Kafka and Elasticsearch. And what we've figured out is that when these applications are deployed in RF3 on the bare metal, compared to Nutanix, it comes out to be way more expensive on bare metal, even after taking into account the resources needed for the CVM as well as the licensing. So we're happy to pick a particular scenario, any of you guys' scenario, and then go over the exercise again, right? So to summarize, Gabe is going to see how we've handled address the bare metal issues with the Nutanix architecture.
So as we went through at the beginning with those bare metal inefficiencies, as stranded resources, over provisioning, you now have the shared infrastructure of Nutanix to basically share those resources that might be stranded in those application silos before. Firmware upgrades and patches are handled by one-click upgrades. Now all those firmware upgrades and everything else are handled by one click, and your applications are able to move around during these upgrades, so there is no downtime for your applications. Single disk failure and node failures are handled by our more resilient infrastructure. When a node goes down, your applications restart on another node very quickly. And when you have a single disk failure, all that does is remove that amount of capacity from that node versus bringing the entire node down. Application teams, now there's a common infrastructure that abstracts away the hardware from them and lets them focus on their application while infrastructure focuses on infrastructure. So in conclusion, run Elasticsearch and Kafka with confidence on Nutanix.
So we have a poll on in the app, and I think everybody who actually does the poll gets
entered for an Amazon Echo.
So we're happy to understand your scenario, see how we can help you achieve the similar performance on Nutanix.
So any questions? There's microphones there if anybody has a question.
So one important point that we want to get feedback on is that if you offer an analytics as a service on Nutanix, right, as a one-click experience, handling both performance, availability, right, with reduced cost, would that be something you'd be interested in?
Basically, raise your hand if it's something you would be interested in. Is management, like setting up performance tuning, how many people, raise of hands, how many people are actually running these applications right now in their environment? Right. And how much time do you end up spending performance tuning and everything like that when you initially set these up? Like Elasticsearch, I know obviously they say every situation is unique.
It's about 3 months to put in Elasticsearch.
Yeah, exactly. So.
And that's because we plug it in for autonomy. We want to pay the autonomy license for that anymore, so we put that out and plug in Elasticsearch. The biggest part of it was not setting up Elasticsearch. It was setting up the integrations with the rest of the application.
Got it.
Right.
How many of these are bare metal, like when you're running, how many of these are bare metal deployments and or virtualized
This is
deployments?
all on Nutanix.
These are all
It's all virtualized.
And which company do you represent, if you don't mind sharing?
Pardon?
Which company do you represent?
I work for Toyota.
Oh,
Toyota, nice.
how about others? Like, are you guys running on bare metal or virtualized? Like I saw from one
It's running on Nutanix, not virtualized. If you go out to techinfo.toyota.com and you look up a document of how to, let's say, replace a spark plug in a Camry, you're using Elasticsearch to find that document.
Ah. Thank you. Any questions?
Anybody else? Thank you.
Good afternoon.